You don't know the song?
No, you're the nerd.
You got to enjoy good humor when it comes around. It doesn't come around often in physics, so got to enjoy it. All right, so for falling objects, we're going to relate the motion of free fall to constant acceleration. The problems we just did were problems that involved acceleration. Well, gravity is just acceleration. That's all it is. Except we know the value of gravity's accelerating motion. Okay? We're going to calculate displacement, velocity, and time at various points in the motion of free fall. And we're going to compare the motion of different objects that are in free fall. So let's begin with this example. Okay, let's begin with this example. So, the first thing I want to start with is this. If I take this pen and hold it here and I let it go, why does it fall? Why don't I drop it also? Why does it fall? Why does it fall? Gravity. Gravity is what causes it to fall. What if I toss it up in the air? It comes to a stop at the top and then comes back down. Again, because of gravity. So, on the way up, as it releases, it's got a positive velocity. It gets to the top. Because it stops for an instant, what's the velocity at the very top? Zero. And then the velocity becomes and more and more and more and more negative, right? Until it reaches what we call terminal velocity. Terminal velocity is when the air resistance pushing up balances with the force of gravity pulling down. And it eventually can no longer speed up anymore. It just moves at a constant velocity. That's a phenomenon with air resistance. We'll talk about that, but for the sake of now, we'll say that when I throw it upward, it's got a positive velocity. It's slowing down and slowing down and slowing down and slowing down and stops. Well, that's this right here. It starts with a positive velocity of 10. It's slowing down and slowing down and slowing down, and after about 1 second, it stopped. Take a look. When it hits the horizontal axis, the velocity is 0. But then what happens afterward? It starts to go in the negative direction, and it becomes faster and faster and faster and faster and faster, but in the negative direction of velocity. What do you think the slope of this line is? What is it?
Negative.
It's negative because gravity pulls which way? Down. Remember the slope of a velocity versus time graph, which is what we have here, is acceleration always. The slope of a velocity versus time graph is acceleration. So the slope of this graph that you see here is really gravity. It's gravity's acceleration. And we'll talk about that number in a moment, what it is. Okay, but the slope of this graph is the acceleration due to gravity. And this graph is depicting me tossing the marker up and it coming back down. Or on the left, the billiards ball going up and coming back down.
So does the velocity start becoming, the acceleration, does it start becoming negative when it's still going up?
So the acceleration is always negative, but the velocity starts to slow down and slow down and slow down until it hits the top, and then it starts to pick up in this direction and become more and more negative. But take a look. The slope of this line is not changing. It's always negative. So gravity is always negative acceleration. Always. Okay? Let's write down what gravity is. The acceleration due to gravity is known as g, which is, anyone? From physical science maybe? Do you remember the number?
Oh, that's the wrong number.
3 numbers and a damn
The dimension?
No, but we have over s squared is more.
Sure, I agree. But it's acceleration,
Thanks
eh?
for letting me win that one. Just a little bit.
A little bit. It's acceleration. Acceleration is always meters per second squared. Velocity of any type is always meters per second. So you don't have to memorize too much now. But we don't write a sub g usually. We use little g. Okay? On your formula sheet, quickly, go to your formula sheet. Look at your formula sheet. Look at the bottom of it. At the very bottom, what do you see at the very bottom of the formula sheet? All those constants, right? The first one of the year, there it is, okay? So if I don't tell you you have to memorize it, you don't. You do not have to memorize it. Trust me, you will. Inherently, you will. Because you're going to do enough of these problems. Let's take a look quickly at the first example. An object is dropped from the top of the Empire State Building. It's dropped. So what's the initial velocity? 0. Remember, it's like this. Ready? No velocity. I let go. It starts to pick up Starts to pick up velocity. I'm going to break the spin in a day. Starts to pick up velocity. So the initial velocity is 0 because it starts from rest. So it's dropped. So we can write VI equals 0. From the Empire State Building, whose height is 443 meters, and lands directly on the ground below. Determine the velocity of the object when it makes contact with the ground. So we know the displacement vertically. Here's what I'm going to start doing. Okay, I'm going to call it y. It's the same thing as x. You know all those formulas we just looked at? Remember how there were x's everywhere? Use the same formulas, but instead of using x, use y, because it's vertical displacement. It's going down. It's going down. So we have to be careful here. Down is negative, up is positive. Acceleration to gravity, we know, is negative. We wrote that a minute ago, because gravity pulls down. So instead of 443, what should I write? Okay, and we'll figure out what the velocity is when it makes contact with the ground, and then we'll also figure out how long it takes tomorrow in class. Okay? So what's the formula we're going to utilize in this problem? Katie?
Would it be VF equals VI? Oh, no, we don't.
We don't have T. See, I'm glad you stopped though. Good. So Katie started saying VF equals VF, let's say T, but we don't have time or VF, so we can't use that one.
VF squared equals VF squared plus square.
And instead of X, since it's vertical, we're going to say Y. Okay, so let's start with this formula. We want to find out what VF is, the velocity, as it's about to hit the ground. VI was 0, so what can I do? What did I tell you guys you can do when it's 0? Yeah, cross it off, please. Okay, drop it off. It doesn't exist anymore. Our goal is to figure out VF. So solving generically for VF, it's the plus or minus the square root of 2a1. Okay? Again, how do I get rid of a square?
Square root.
Square root. Plus or minus because we're taking a square root. Look at your numbers. Let's see what we get for this first one. If I am correct, you just had a test about imaginary numbers, didn't you?
We didn't get tested on that part.
Is this going to be an imaginary number though?
We did.
Yes,
No.
yes, because it has a square root.
No, it's not going to make it
Right.
It's going to be positive.
It's 2 negatives.
minus.
No. It's 2 negatives.
So that's positive.
So this ends up being square root of a positive quantity here, not a negative quantity. Okay, this ends up being the square root of a positive quantity here. So what is the answer? What is the answer? What is the answer?
93.2 meters per second.
Positive or negative, Anthony?
Positive.
Which one? Why?
Huh?
Why?
Because it's the velocity is negative, it's not going back. I'm not sure. Because there are two negatives, that's the math reason, but I don't know, like.
Be careful. Think about the physics of the problem, the actual common sense of the problem, right? Let go of it. Which way is it traveling? So it's actually going to be
Negative?
negative. And it's all, remember, it's all arbitrary. So I took a physics course, and my physics teacher, to mess with us, spent an entire chapter where everything down was positive, but the negative was up. It's the same thing, it's arbitrary. As long as you're consistent. See how we called G negative 9.81? If I said, and I told you that down was positive, then G would be positive 9.81. So it depends on what your coordinate system is. You pick the coordinate system yourself. I recommend that you consider down negative and up positive because that's the most common sense. Okay? But it really doesn't matter. As long as every time you do down it's positive and up is negative, you can do that also. But I'm going to instruct you guys that I recommend you consider down negative.
Just like theoretically, Cheryl, like common sense, would you, and the answer was negative, would you have to just make it positive just because it's the question? Or
No, it would have to come out positive for that kind of problem. Okay, it really depends on the context of the problem. Like when are you finding the velocity? If it's going up, are you finding the velocity right now? right now, when it stops, when it's on the way back down. So there's a lot of other questions you have to answer before you can choose the negative or positive correctly. That is the velocity of the object when it hits the ground. That is around 200 miles an hour. So think about that. The Empire State Building, you drop something off, it picks up enough speed to get up to around 200 miles an hour. Now, what is that neglecting though? Air, what is it? Wind or air resistance, we'll use, right? Resistance. There's what's called drag. Drag is air resistance on a car, on a vehicle, or an object in motion. So although this is around 200 miles an hour, it's probably a little bit less because air resistance slows it down on the way down. Okay, air resistance pushes back up, even though gravity is pulling it down. So air resistance would cause this object to not get this fast, actually. But it's still around 200 miles an hour. Okay, that's why they had that old tale where if you drop a penny off, it'll go into someone's head, like it would embed into their head. And I think somebody said on Mythbusters, they tried to prove it, and it just breaks the skin. It doesn't actually break bone though. But if you drop an object, a penny has no mass to it. You drop a heavier object that has more inertia, that will easily crack someone's skull if it came off the Empire State Building. Part of the reason they really don't allow you near the edges and stuff, and the shape of the building is toward the tip, right, like this. So when you're at the top of the viewing deck, you can't really throw something off the edge. Okay? How about the next part? Time. Time. How long does it take for this object to reach the ground? What formula can I utilize? And this was the formula that Katie started mentioning, and then recognized that we didn't have time, so we couldn't figure out VF. But now we have VF, so we can figure out time. What's VI again? What's the initial velocity if it's dropped? Everybody. 0. So I get VF over acceleration is equal to time. Remember, if this is a 0, this equation simply becomes VF equals AT. And then I solve generically like that. Okay, it becomes VF equals AT, divided by A, you get your answer. Take a look. VF is negative, A is negative, it's not a coincidence. It makes time positive. So what do I get for my time in this problem? What do I get for my time? Now, at this point, I'm going to ask everyone to pause and take out a calculator if you haven't done so already, because I'm seeing a lot of missing calculators. I told the other class, next week I'm going to start a point off your test for that test if you forget a calculator from now on. A full point. You need to have it every time. Now, yeah? 45.2. Are you certain?
Oh, wait, I did it wrong.
93.2 over 9.81. Okay, Honor, help her out. 9.5 seconds. If I'm rounding to the nearest tenth.
Yeah.
Okay, so 10 seconds. Isn't that crazy? Think about that. 10 seconds from the Empire State Building for it to drop. All because of gravity. Gravity. Only 10 seconds to fall down, the entire drop. It's a huge distance. 443 meters, that's like 5 football fields. A meter is larger than a yard. So it's about 5 full football fields. So huge displacement.
Later in the year, will we have to account for air resistance and stuff?
So that question was posed in the last class. The problem with air resistance is in order to actually account for it, you need to use some calculus. And right now, you haven't taken calculus yet. So we'll talk about it and what it does. Like specifically here, if I accounted for air resistance, would the time be longer or shorter? Why? Yeah, it's slowing the motion of the object. So if air resistance were considered, right, this would take a longer time period. So that's a great multiple choice problem, isn't it? For a test or something like that? Very good one. Okay, let's take a look at the second example. Not get intimidated. We will break it down to pieces, one at a time. Ellie, read for us, please.
A toy rocket is launched with an initial velocity of 25 meters per second straight up.
Read parts A and B, please.
After how much time will the rocket reach its maximum height? What is the rocket's maximum height?
Okay. Why am I not reading part C and D? Take a look at that. See why I don't care about part C and D just yet.
That's what's returning now.
It's on the way down. So what am I going to focus on? Parts A and B on the way up. So we call this truncating a problem. We're just splitting it into parts. So we're going to do part one. Part one, on the way up. So draw yourself a projectile. It goes vertically upward, and it ends up here for a split second, and it stops at the top. This is part one. So this is initial, and this is final. Okay? Initial and final. So what's the initial velocity in this problem? Yeah?
25 meters per second.
Yeah, positive 25 meters per second. It's definitely the initial velocity. Now, for this truncated portion of the problem, what's the velocity when it reaches its final position? 0. Again, it's at max height. We're considering max height to be the end of the problem. The problem is over. We don't care about the way down. So at the max height, the velocity is indeed 0. What else? What else? I know something always for vertical motion. What do I always know for vertical motion?
9.8.
Be careful. Negative. Okay? Negative 9.81. And we're trying to find out the time. Another pretty easy formula to utilize. Which one should I use here? Someone who hasn't answered yet today, please. What formula should I utilize for this problem? For this problem, what formula should I utilize? Emma, you got it? It is indeed. And Emma knows that because you're looking for time in part A. You got BF, you got BI, you got A. So go ahead and solve, right?
Could you also use A equals delta V over T?
Yeah, it's the same formula as this. Absolutely. You could always utilize that one. Remember, VF is 0 here. That drops off. So what's the generic solution for for T? Be careful here. This can be a little tricky, the algebra involved. You got to get rid of VI first. How do you get rid of VI? Think of it as a number. Subtract it. So the left-hand side is going to be a negative VI equals AT. Remember, subtract VI from 0. God bless you. It becomes 0 minus VI. By the way, I heard Siobhan sneeze for the first time today. And everyone went, oh my God.
She has to find the need to scream.
So we then solve for time. It was just funny because you guys mentioned it last class, and it happened today. We divide by A. Divide by A. A's cancel. So time is negative VI over A. It's not a coincidence that it's negative over negative.
Because it's a positive.
Good, because time has to be positive. What is the deal? 2.55 seconds. Very good. 2.55 seconds. Okay? So far, so good. All right, nice, nice. Let's see. Part B. Part B. We're now trying to figure out, I don't even remember, how long? Yeah. Oh no, height. That was how long. The height the rocket attains. What variable is height? Y. D is distance, right? Don't forget. Okay. Y is vertical displacement. The variable Y is vertical displacement. So now we want to figure out what Y is. What formula can I use? What formula can I use? Let's figure out.
Could you use like V bar
It's a good question you asked that. Somebody in the other class got that too.
This can be like replaced by X.
Why can't I use that? Anybody know why I can't use V bar equals X over T?
Oh, because it's not like
Yeah, because that could be used for vertical motion technically if there were no something. What are we not taking into account if we use V equals X over T?
Acceleration.
Acceleration, remember? These problems all involve acceleration. That first formula of the year, it negates or neglects to use acceleration. If there was no vertical acceleration, we could technically use it. We're never using it vertically because it's always acceleration vertically. So what's the other one that is?
V squared equals VX squared plus 2x.
That works, but there's an easier one for sure. Because it's not solved for X there.
Oh, X equals VIT plus 1 half AT squared.
Okay, so Y instead of X, same thing, equals VIT plus 1/2 AT squared. Okay, recall that VI is, what was VI in this case? No, VI is not 0 in this one. Remember, VF was 0. VI was 25 times 2.55 plus 1/2 times negative 9.81 times 2.55 squared. What do you get? What do you get? What do you get? And your answer should be positive because this object is moving which way? It's going up. It's going up. Honor.
31.85.
Good. Units are what? What are the units? Meters. Good. Okay, 31.85 meters. Questions at all on this part of the problem? Okay. Now, if that is the case, and we want to evaluate part C, somebody read for me, please. Alejandro, read part C for us.
What will its velocity be when it returns to ground level?
So now we're worried about which part of the trip? On the way down. So let's go ahead and redraw this diagram. We still have some information we can use, like the displacement there, we can use that for part C. But for part C now, here's the object. It's at max height, it's not moving, right? It made it to max height, it stopped, and now it goes down until it hits the ground at the bottom here. So the VI in this problem is now what? 0. Nice job, Emma. Okay, we have to consider now that when it's at the top now, it's the initial part, and at the bottom is now the final part where this object lands. Is that clear what I'm getting at? This is the second portion of the problem. On the way up, the ground was VI, the top was VF. But now we're looking from the top back down. So now we start the problem over. This is now VI at the top. It's like we're dropping it. It's pretty much like the one from the Empire State Building. And it comes back down to the ground. We're going to see that there is symmetry, but we need to prove it before we can assume it. You're right to assume that, actually, Ellie. There's going to be symmetry. But let's prove it mathematically, then we'll assume it afterward. So if I know this is true, what is the displacement going down? Negative what? What's the number we had from the last part? That's the acceleration. Be careful.
Oh, is it the 31?
Yeah. So the displacement is the same displacement. If the rocket makes it up to 31.85 meters, to go back down, it's got to travel 31.85 meters down. Okay? And again, we knew VI was 0. That's up here already. We already stated that fact. Right up here. So our goal is to figure out the final velocity at the end of the problem. VF squared equals VI squared plus 2AY. VI is 0 this time, because it's like it's being dropped from rest, because it came to rest at the top there. What do I get for VF in this problem? What do I get for VF? It's definitely plus or minus because there's a square root involved. What's the number turn out to be in? What does the number turn out to be?
It's 24.99, so like 25.
Yeah, it is 25 actually. Very good that you noticed that. It's the rounding that we did earlier that's causing that issue in the square root. Is it plus or is it minus? Why? Yes. Right? Here's the rocket. It's launched with a velocity of 25 meters per second. It comes to rest. It then picks up the same amount of speed on the way down, but in the negative direction. So it's the same answer as the beginning of the problem, except for the fact that it's a negative velocity. So there is, as Ellie stated, symmetry in the problem. It was launched with a velocity of 25. It lands with a velocity of negative 25. Okay, part D. Part D. Part D, we're trying to figure out what? I don't even remember what part D said. How long will it take the rocket to return from max height to ground level? What's your guess? What do you think the answer is going to be? Symmetry. What do you think the answer is going to be? 2.55. Okay, let's prove it. Let's prove it true. So, to find out the time when it hits the ground, again, we know at the top the velocity was 0. We know the velocity at the end was negative 25. And we know the acceleration is negative 9.81 meters per second squared. I go ahead and I solve. Vf equals Vi plus At. Vi is 0. To get time, it's again Vf over A. This gives me negative 25 over negative 9.81, which again is the same answer as before, 2.55. So you want to make sure that you recognize that there is indeed symmetry in the problem. Okay, we definitely have symmetry involved in this problem. Now, just to prove the symmetry, I want to prove it to you that there is symmetry. Okay, so I want to go ahead and take a look at this problem from a different lens. And didn't break it into pieces. What if I consider this the beginning, right? It gets launched, comes back around, and hits the ground. We're going to consider that the end. Let's do that instead. And you'll see the symmetry here. So, the initial velocity is 25 meters per second. So we're redoing this problem real quick, but we can do it all in one piece. That's the initial velocity. The acceleration is still the same. It's always the same in the vertical direction. Now, if I launch it from the ground, and it comes back around and hits the ground, what else do I know? Very good. Displacement is 0. Displacement is 0. A moment ago, we got 31.85 for the displacement up to max height. But if I'm not trying to find max height, and I'm just trying to prove symmetry right now with velocities, I can do the whole problem neglecting the max height. Who cares about it? Now we can figure out what Vf is. And it's so obvious now. Watch, here's why. Here's your formula, right? What drops off this formula? What drops off this formula? Yeah, which part drops off? No. Where's the 0, guys? Isn't y 0? Put the 0 in here. What does it make this whole thing? So what do you get, Katie?
Just get VI. You get the square root of VI. So equals. So VI equals 25.
So you end up getting 25. Because think about it. If you square it, you get 625. And then you go back to the square root. Well, what's the square root of a square? It's just that number itself. Okay, so in the end, you end up getting this right here. I'm going to box it in. Okay, you get this statement pretty much, because that drops off. Square root both sides, you get Vf equals Vi. But you need to remember the plus or minus. Because remember, it turned out that Vf was the same, it was 25, but Vf was negative when it hit the ground. Okay, so this proves the symmetry of the problem. The same thing occurs with time. Proving the symmetry with time, we could say the following. Let's see. Take a look at this now. Since we know Vf was negative 25, just the opposite of Vi, we can plug them in. And what we'll get here, instead of negative 25 over negative 9.81 that we got earlier, we're going to get negative 50 over that. So you're going to get double the answer for your time. Why am I going to get double the answer for time now? Why am I going to get double the answer I got before? Before I got 2.55.
Because it goes up and it goes up.
Exactly. 2.55 up, 2.55 down will give you 5.1 as your answer for this problem. Okay, so the entire trip takes 5.1 seconds. Earlier we got 2.55 up, 2.55 down, proving the symmetry in the problem. Okay? Now that you know that there is symmetry, you can utilize that notion. So if I give you a multiple choice and tell you that something starts at ground level, gets launched, and returns to ground level, you can tell me that the velocity when it hits the ground is the same as when it was launched, except it's negative. If I tell you it takes 3 seconds to make it to the top, and it takes 3 It takes 3 seconds to make it to the bottom. No negative time, remember? No negative time.
Oh, sorry.
So the total trick would be 6 seconds then, right? So this knowledge you can now utilize, assuming it starts where it ends. If it starts here and does this, and is there going to be symmetry anymore? Because the problem is not symmetric. The geometry is not symmetric. That will be our last example right now. Let's take a look. Nice and loud for us, please. Frankie, go for it this time.
Jason hits a volleyball so that it moves with an initial velocity 6.1 in a second, straight upwards. If the volleyball starts from 2.1 meters above the floor, how long will it be in the air before it strikes the ground?
Now, we're trying to figure out for this problem the fact that it's starting at a certain height but ending at a lower height. How many people play volleyball here? I know you play 2, 3 ladies? Okay. So, this is obviously not really feasible because you would never hit the ball straight up. Actually, no, you would set it, right? A second straight up. So imagine like a 6-foot person, 2 meters. They go for a set, they set it straight up, and the other person comes in to spike it and just misses. Well, where is it going to land? On the ground. So that's literally this problem. It starts at 2 meters, it goes up to some height, we don't care about that height. We don't know how long it will take before it hits the ground. So can the person, Libero, right? Libero in the back, can a Libero come in and dive in time, pretty much? Can they make it there? So, in this problem, we know that we have a visual of this. Ready? It's like an object that's starting at a level, like a cliff, if you will, that gets launched up, and it comes straight back down and ends on the ground down here. So what is the displacement in this problem? What is the displacement? The displacement in this problem? Now, what's the displacement here?
0.
It's not 0. It's not 0. Remember, it's starting and ending lower than it is. It can't be 0. It would have to end where it started to be 0. Class? Negative. Yeah, negative. What number though? Yeah, the number. Negative 2, right? Good. So it's negative displacement. That's the important part there, right? Negative 2 meters. How do I know that? In case you forget, final minus initial. The final height is 0. The initial height was 2. 0 minus 2 is negative 2. Your final minus initial. Okay, so negative 2. Any questions on that? Let's continue. We know the initial velocity was straight upward and it was 6 meters per second. So the velocity was set straight up. So the velocity is positive 6. We want to know how long it will take to hit the ground. At this point, by the way, I'm going to keep filling in acceleration always. I shouldn't even have to ask that one.
Always negative.
For any vertical motion, it is always negative 9.81. For any horizontal motion, it's going to be 0 always. Gravity doesn't act left to right. Unless I tell you an object is accelerating left to right with a velocity. Because we're going to see in the next chapter how projectiles move. Okay, and we're going to assume acceleration in the x is always 0. But for now, y direction is negative 9.81. So I need to solve this, right? I need to go ahead and solve this. What equation can I use? Be careful. I don't know anything about VF. So there's 2 equations I can't use. Sierra, what am I going to use?
X equals VI t plus 1/2 AT squared.
Good. Y equals VIT plus 1/2 AT squared. I can't use the other ones because I don't know VF. I could use the other ones, find VF, then use another formula and find time. I'd have to do 2 formulas for that. Instead, I could do it this way and use my handy-dandy quadratic formula in a minute. Let's plug in what we know. We know the displacement is negative 2. Velocity initially is 6. Time is unknown. Plus 1/2 negative 9.81 times squared. Why am I going to use the quadratic formula here? Why am I going to use the quadratic formula? Come on, you have Miss Rusi. Phenomenal Miss Rusi. Or you have You have a quadratic equation. T squared and t. It's a quadratic. Had this not been here, the 6t, make believe that's not there, then it's easy. Multiply by 2, divide by acceleration, take the square root. You can do it. But when that t is there, next to the 6, that screws everything up. So let's move things over so we get a 0 over here. What's half of negative 9.81? It's negative 4.905. That's a number that you're going to start to memorize. You don't have to, but it'll just come up a lot. Plus 2 on the end there. Now, is this in standard form? It needs to be in standard form. Decreasing degree. So what goes first in a quadratic? Ant? Yes?
Negative 4.905 c squared.
Go ahead. Plus 6t plus 2. So I've taken the equation above and put it in standard form. Okay, now, we're going to run out of time. We have to do the people stuff in a minute. So, I'm just giving you a heads up. The quadratic formula is
Negative b plus or minus the square root of b squared plus 4ac over 2x.
very good.
X plus
Yes, very good. You remember that. I saw in that freshman year in terrible voice. Good. It's the pop b squared minus 4ac. Sorry. B squared minus 4ac. Okay, now, before we begin the next part, I want you to listen carefully. I continued and finished this in the other class by plugging in numbers. When you do the quadratic formula, you get how many answers? You get 2 answers. Not necessarily. Hold off that. The plus or minus indicates that you're going to add something and you're going to subtract something. But they could both be positive. In this case, you end up getting answers of 1.5 and negative 0.2. Can't be negative time. Reject that answer. So your answer is 1.5 seconds. Now, there is also a way to solve quadratics using your graphic calculator, using the y equals graph command. I'm going to put a video up for that. Okay? It'll be a YouTube video that I'll just find where that works that somebody's already made. But I'll put a link to that under videos from class. So look if you want to see how to do that on your calculator if you don't want to use the quadratic formula. I don't care which one you do, I really don't. But I want to see the original equation like this set up. And then if you use a graphic calculator, you need this. Okay, you can do it all on the graphic calculator. Okay, but instead of t, whenever you use the calculator, you use x. It's really the only difference. But I'll put up a video on how to do that part. Is that clear? Okay, so tonight, over the weekend, you should finish up the homework or do the homework from 2-3. There was a problem in 2-2 that involved vertical motion. If you couldn't solve it, it's okay. Try and do it over the weekend also. On Tuesday, your problem sets are due. On Wednesday is our first test. Okay, next week, we're going to have a lab on Monday. We're going to have review and the other part of the lab on Tuesday. And then the test is on Wednesday. Okay, so next week will be a lot of review for the test because the lab helps for the test a lot. The new lab we're going to do next week will help you to understand the graphs. Remember the graphs we did a lot of? For the test. Right? I just got instructions for this stuff to do, so give me a minute to look. Please sit quietly so I can actually do this with sanity.